Okay, so for this question, what I've done is drawn a sketch, first of all, the sketch that we're given. And we need to find out then what the least value of the coefficient of friction mu is going to be in order for this plank then to stay in equilibrium. So we need to put on some forces on here, first of all. So what would the forces be? Well, first of all, it's a uniform plank of length 4 meters. So in other words, 2 meters from the end, in the middle of the plank, the weight is going to act, and that's going to obviously act downwards. So if we just mark that in there, we're told it's of weight 100 newtons. So we'll just put 100 newtons there. What other forces would act on this? Well, the plank is at rest on this smooth cylindrical drum, so there's going to be a contact force, a normal contact force. Let's just have it coming out there. Normally I'd give contact forces as R newtons, but since it's at C, we might as well put a little subscript there, RC newtons then. Now, because it's a smooth cylindrical drum, there's going to be no friction here, so that'll be the only force acting at C on the plank. The other forces are going to be at A. This is on rough ground here, so there's going to be a contact force, a normal contact force, which we'll have up here. That too would be an R for a reaction there, but because it acts at A, let's just call it R with a subscript A, newtons. And this plank would want to move out towards the left, so if there's going to be friction, it's going to oppose motion and it's going to act towards the right here. We'll call it F, okay? F newtons. Now, we know about friction. Friction is related to the coefficient of friction through the equation F equals mu r. But it only reaches that value, that limiting value of friction, when this is on the point of sliding or is actually sliding. So what we know, if this is in equilibrium, that F must be less than or equal to mu r, r being Ra in this particular example. So if we're to work out what the least value of mu is going to be, then we need to work out what this value of F is and what Ra is. And that's our starting point then, really, okay? Trying to get F and Ra. Now, to get Ra, I would want to possibly think about resolving vertically, because that would include Ra into the equation. So let's start by resolving vertically. So if we resolve upwards then, taking upwards as positive, what we've got is that all of Ra acts upwards, so that's in there. And then we've got the weight acting downwards, minus 100. Obviously F doesn't enter the equation because it's perpendicular to the direction we're resolving in. We also have components, a vertical component coming from this reaction here. If we mark in with a dotted line upwards, okay, we can split this force RC into a component upwards and a component towards the left. But to do that we need an angle, and we should see that this angle in here has to be the angle alpha because these angles are alternate. This dotted line here is parallel to the ground here, so these alternate angles. This angle in here is 90 degrees, so that must be 90 minus alpha. This angle is 90 degrees, so this must be alpha again. So if we just mark that in as alpha. So when it comes to the vertical component given from this reaction here at C, that vertical component is going to be RC cos alpha, and it's acting in the positive sense, so we've got plus RC cos alpha. They're the only forces then acting in the upward sense, and because the plank is in equilibrium, this must equal 0. Okay, well, we're not going to get very far with this now because we don't know what RC is. So we're going to need another equation. So we'll just put this on hold for the moment and call it equation 1. So normally if we resolve in one direction, we can expect to resolve in a perpendicular direction. So what I'm going to do now is resolve horizontally. And I'm going to take to the right as positive, but obviously it doesn't matter. You can do it whichever way you want, as long as you stick to the sign convention. It should all work out in the end. So if we resolve to the right, we've got all of F acting to the right, the frictional force. What else have we got? Well, RA won't come into the equation, nor will the weight, because they're perpendicular to this direction. But we've got the component to the left here from this reaction at C. So that's going to be minus, because it's acting in the opposite direction to this, minus RC sine alpha. And that is our resultant force on the plank in the horizontal sense. And because it's in equilibrium, it's going to equal 0. And again, we'll put this equation on hold, alright? Call it number 2. For our third equation, because we've got 3 unknowns so far, we've got RA, RC and F. We know about alpha. We're told, by the way, that sine of alpha equals 1/3, so we can use that later on to work out things like cos alpha, etc. Okay, but we got 3 unknowns, so we need 3 equations, 3 independent equations, and we get that next equation by taking a moments equation. And you can take a moments equation about any point you like. I'm going to choose A though. Alright, why? Because most of the forces pass through here, and it just means that I don't have to include RA and F into my moments equation, because they would have no effect in turning the plank about A. And I also need to set up a positive sense, and again that can be any way you like, but I'm going to choose anti-clockwise. Do experiment with this kind of question, choose other directions, other points, and that's the way you're going to gain confidence when you're doing these kind of questions. You should end up with exactly the same results at the end of the day. Okay, so if we're taking moments about A, then as I said earlier, these 2 forces don't come into play. But if we start with RC, we can see that RC at the moment is perpendicular to AB. So it will be the force RC, which will want to turn it in an anti-clockwise sense. So it's going to be positive moment. So it will be the force RC multiplied by the distance C to A, which we know is 3 meters. So we'll just put RC times 3. So that's step 1 done. Now we go to the weight. Okay, now the weight is not perpendicular to the plank, so I can split the weight into 2 components. One in this direction, perpendicular to the plank, and the other one straight down the plank. Okay, now we know that this distance from A to where the weight acts, it's in the middle because it's a uniform plank. That distance must be 2 meters. We also should know that this angle is angle alpha. So when we split the 100 newtons into 2 components, one in this direction and one down the plank, the one down the plank passes through A, so there's going to be no turning effect produced by that force. The only turning effect that's going to be produced is this component, okay, of the weight. And it's going to want to turn the plank in a clockwise sense about A. So it's going to be minus then for that one, and the force will be 100 cos alpha. So we'll just mark that in as minus then 100 cos alpha. That's the force, and we now need to multiply it by that distance to A, 2 meters. Okay, so that's being multiplied by 2. So that's the total moment on the plank, but because the plank is in equilibrium, that total moment must be equal to 0. Now from this equation we could work out quite easily what RC is. because it's really the only unknown in this equation. So therefore, if I rearrange this, we've got 200 cos alpha here. If I add that to both sides and divide by 3, I get that RC equals 200 cos alpha all divided by 3. Now, we could either work out cos alpha by getting the angle, doing the inverse sine of a third, and then doing the cosine of it and substituting it into here, or we could keep it in exact form. When you get something like this, sine alpha equals a third, a ratio, that prompts me to draw a right angle triangle. What I'll do is I'll draw that triangle in here just to save a bit of space, okay? I know it's a bit cramped, but there's a lot to put in this question here. But if this angle is alpha, the sine of alpha compares the opposite side to the hypotenuse, so that'd be 1 over 3, 1/3. And by Pythagoras' theorem, we can work out then this shorter side as being the square root of 3 squared minus 1 squared. Square root of 8, in other words. Root 8 is also 2 root 2 when it's broken down. So cosine of alpha then will be 2 root 2 over 3, adjacent over hypotenuse. So if we come down here, we can start to fill in the remainder of this question. So we can say that therefore RC is going to be equal to 200 over 3 multiplied by the cosine of alpha, which as I said was 2 root 2 over 3. So let's just pop that in there, 2 root 2 over 3. And if you work that out, what you get is 400 root 2 over 9. So there's our contact force at C, and that's measured in newtons. Let's call that that result there 3. Okay, we're going to need that later. In fact, we're going to need it now actually, because what we could do is substitute this into equation 2 and we'd find out what F was. Okay, so if we just say sub 3 okay into 2, then we've got F minus RC sine alpha. RC we've seen is 400 root 2 over 9, and that's being multiplied by the sine of alpha. Sine of alpha we know is 1/3, so we can multiply that both a third and it equals 0. So what we've got here is 400 root 2 over 27, and if we add that to both sides, we therefore have that frictional force F is going to equal 400 root 2 over 27. And that too would be measured in newtons. Okay, well, we've got F. Remember, we're trying to work out what this least value of mu is. So we need F and we need the normal contact force at A, RA. And to get RA, we've got to now go to equation 1. So we can substitute our result up here for RC back into 1 and get what RA is. So if we say sub equation 3 into equation 1, what we're going to have now is RA minus 100, so we'll have RA minus 100 plus RC, which is the 400 root 2 over 9, okay, multiplied by cos alpha, so 2 root 2 over 3, multiplied by 2 root 2 over 3, and that equals 0. So if you add 100 to both sides and subtract this value, either do it on your calculator or you could do it in your head, you'd end up with a total of, well, RA would equal 1100 over 27, okay, newtons. Okay, so we've now got all that we need. We can now go back to this equation here. We can say that since F, the frictional force, must be less than or equal to mu RA, if we were to rearrange this for mu, it follows that mu must be greater than or equal to that frictional force F divided by Ra. So therefore mu must be greater than or equal to F, which is up here, 400 root 2 over 27, and that result is all divided by Ra. Okay, and Ra we've got here as 1100 over 27. So if you work that out, what you get is that therefore mu has to be greater than or equal to 4 root 2 over 11. That's the exact value. Or you could put it as a decimal. If you went for a decimal, it's greater than or equal to 0.5142 and so on. So in answer to the question, what's the least value that mu could be? Well, therefore we can just squeeze it in here. The least value, okay, of mu is going to have to equal 0.51 to two significant figures. Okay, 0.51 to 2 SF. Okay, so there you go. That brings us then to the end of this question.